Alright, so in the last class we were looking at two different implementations of data flow graphs, one of them for an FIR filter, the finite impulse response, and the other one for the IIR or infinite impulse response filter. And what we concluded from sort of looking at the iteration periods over there is that as far as the FIR filter was concerned, it is in principle at least possible to reduce the iteration period indefinitely. In other words, you can bring it all the way down to 0 provided that you have sufficient hardware available to you. Okay? Whereas in the case of the IIR filter, that's not possible. Even if you have access to infinite amounts of hardware, the very nature of the graph beyond a point is going to put a limitation and therefore restrict how much you can reduce the iteration period. Okay? So what we are going to do now is to see whether we can actually come up with a way of theoretically estimating what the ideal iteration period bound of a given system is. Okay? So the assumption that we are going to make is that we have a digital signal processing system and it has been represented in terms of a data flow graph. Okay? And every node or every actor in the data flow graph, we have access to some kinds of hardware. Some hardware is available for each and every actor present in the data flow graph. Okay? Now this is an assumption which in turn will impact the estimates of the iteration period bound that you get. So one thing to keep in mind over here is when we are deriving this iteration period bound, okay, so that's the term that we are going to use. The iteration period bound is what is the minimum iteration period that can be implemented for a given data flow graph, assuming that you have infinite amounts of hardware. Okay? But in addition to that, there is one more assumption that we are making over here, namely that the hardware itself is of a certain type. So when I say that there is a hardware realization, what I mean is if I need to add two numbers, I assume that I have a certain piece of hardware that is capable of performing two input addition and it has a certain delay associated with it. Okay? So that delay could be in nanoseconds, it could be like half a nanosecond, 1 nanosecond, 10 nanoseconds, whatever, or it could be in clock cycles. So let's say that I have a serial multiplier, it might be something that takes 10 clock cycles, in which case my unit of time essentially is going to be clock cycles. Right? Why I am saying that is it's important to understand that on the one hand, the unit that is used in order to represent your timing or to represent the delay associated with a piece of hardware is not important. But what is important is that you are making an assumption that your hardware has certain delays associated with it and the amount of delay is dependent on that hardware. Okay? So whatever iteration period bound that you compute is dependent on two things. One is your data flow graph itself, and secondly, what technology you are using, what kind of hardware elements you have. Okay? So if you move to a better technology, let's say that you go from 180 nanometer to 90 nanometer or 45 nanometer technology, presumably every single hardware unit, your adders, multipliers, etc., will become faster, and therefore your iteration period bound comes down. Okay? That is not our concern. Our assumption is that you are working within a given technology, your hardware is therefore restricted according to that, and subject to that, what is the iteration period bound? That's what we are trying to find. Okay? Subject to these assumptions, right, what we can sort of say is what we are going to do is to draw up a set of what we are going to call constraints, okay, and to perform essentially some kind of constraint analysis. Okay? So an example of a constraint is simply something like this. Let's say that I have two actors, A and B. Okay? I don't care whether these are adders, multipliers, FFT blocks, adaptive filters, right, complete image recognition blocks. I don't care how complex A and B are. The only assumption is A is one self-contained data flow block, meaning that it performs in a data flow manner whenever it receives inputs, if it has any. In this case it doesn't seem to have any, but whenever it receives inputs as required, it is capable of generating outputs. Okay, there is no other sort of constraint, no other requirements for it to function. Whenever it gets data, it can then consume that data, operate on it and produce outputs. Similarly, B is also of the same type. That's the only assumption I am making. Okay. So with that in mind, A and B are two arbitrary actors. I am going to make an assumption that D subscript A and D subscript B are the execution delays of these units. Okay. So this is where the hardware assumption comes in. I am essentially assuming that I have some kind of hardware, be it a adder or a processor that is capable of executing code, whatever, something that will take dA units of time in order to complete the one execution of A. Okay. So dA and dB are, I am going to call them the execution delays of A and B. Okay. Now I am going to introduce two variables, XA and XB, and I am going to say that these are the starting times of some iteration of A and B. Why am I putting some within quotes? Because the assumption over here is that the iterations are infinite, right? These are DSP systems. As long as data is present, they will continue to execute, they will consume data, they will do something and they will generate outputs. So I don't really have a precise starting point. Okay, so I need to arbitrarily define some point in time as my starting point. Rather than just saying a time, I am going to call it an iteration number. Right? In the previous cases, we wrote down basically iteration 0. So I would say A0 was the first iteration of A, A1 is the second iteration and so on. So you can call it that if you like. So you can say the 0th iteration if you like. Okay. So XA and XB essentially refer to the starting time of that 0th iteration of A and B. Okay. Given this much information, dA and dB are known, they are given to you. Okay? You do not have to calculate anything over there, these are just numbers that are given to you. A and B are some kind of actors in the signal processing graph, you do not care what the functionality is, you only know that the output of A is consumed by B. XA and XB are unknown and you want to find out what they are. Okay? What can you say about the relative values between XA and XB? Can XB be less than XA? Let us start with that. Right? No, that does not make sense, because the implication of drawing a diagram like this, where I show that the output of A is being consumed by B, is that only after A has finished execution, B has the data ready for it to execute. Okay? So we can go one step further and we can make a stronger statement. Not only is it that XB must be greater than XA, XB must be greater than XA plus DA, right? It has to wait until A has finished. Okay? So we can basically write down this statement over here, XB is greater than or equal to XA plus DA. I am going to allow the equal to under the assumption that as soon as the data is ready, it can start executing. Okay? This, in other words, is the fundamental constraint that I have with regard to this pair of actors in a data flow graph. Okay? XB must be greater than or equal to XA plus DA. Okay? Alright, let us take this further. What if I now had once again two actors like this, right? Same DA, DB and all, I will assume, I am not going to write them again. But now there is a token over here, right? A token, or this is where the terminology can get a little confusing. I sometimes also call this D as a delay element. So I will try and avoid that terminology as far as possible, I will just call it a token. The reason why it is sometimes called a delay element is because it is a one sample delay. Okay, so if you do come across that terminology used somewhere saying that there is a delay element between A and B, what it means is that this is a one sample delay. In other words, if A is producing x of n, B is not consuming x of n, it is consuming x of n minus 1, the previous output of A essentially. Okay. So if I have one token like this, one sample delay on that edge between A and B, now what can I write about xb and xa? What would you say over here? Now do I still require that xb must be greater than or equal to xa plus dA? It is no longer so clear, because xa plus dA is the time when the nth iteration of A is completing, but B is not waiting for the nth iteration of A, it is waiting for the n minus 1th iteration. Okay? So here I need to introduce a new value t, which I will call the iteration period. Okay? And essentially iteration period t over here is sort of saying that this is the, you can call it the average time if you like, but essentially the time between iterations. Okay? And ultimately what we are going to do is estimate what is the minimum possible value of t that I can successfully use, and this is essentially going to be my iteration period bound. Okay? The minimum value of t is what I am looking for. Now if I have a certain t and I say that this is my iteration period, effectively what I am sort of implicitly conveying by that is to say that if the nth iteration of A finishes at some time ta, the n minus 1th iteration would have finished at ta, would have finished by ta minus t. Okay. So in other words, I can write down this constraint as xb is greater than or equal to xa plus dA, which is the time of the nth iteration finishing, minus t. This minus t essentially allows me to say one sample delay, one sample earlier, what was the time when it would have completed. Okay, which means I can now generalize this and say, instead of one sample, if I had n sample delays, what would the constraint look like? Xb must be greater than or equal to xa plus dA minus n times t. Okay. So this t is just introduced as a new variable, a metric that we want to compute, which essentially allows us to say that this is the time required for completing one iteration. Okay. So if you want to find out at what time the previous iteration completed, just subtract t. 2 previous iterations, subtract 2t, n previous iterations, subtract nt. Okay. So in this way we can see that if I have n delays or n tokens sitting on that edge between A and B, the constraint that needs to be satisfied over there is xb is greater than or equal to xa plus dA minus n times t. Okay. Good. How do we take this forward and now see whether we can come up with an actual constraint? What should the minimum value of t be? Okay. So let's first of all look at these graphs itself. So I have one, this is, supposing this is the entire graph, right? There is A whose output is being fed to B with n delays on it. Okay. xb must be greater than or equal to xa plus dA minus nt. Okay. That's the only constraint I have available to me. Under these conditions, is there anything you can say about what should be the minimum value of t? What can be the minimum value of t for which I can, so what am I trying to do? I want to be able to find some value of xa and xb such that this condition is satisfied. Okay, that's all I am saying. All that is given to you is dA and dB and n. Those three values are given to you. t you do not know, I am asking you to find out what is the minimum value of t, and xa and xb you do not know. I am asking you to find any possible values of xa and xb for which this condition can be satisfied. Okay. So, first question, can t be negative? That does not make sense, right, because by the very nature of the iteration period, it is sort of saying that this is the time between one iteration and the next iteration. So, by definition pretty much it has to be non-negative. Okay. So, now that we know that t must be greater than or equal to 0, the question then becomes, can t be 0? Okay. And yes, if I set t equal to 0, I can just pick any value that I want for xa. For simplicity, just choose xa equal to 0, right. Let t equal to 0, let xa equal to 0, any value of xb greater than or equal to dA will satisfy this constraint. Okay. So, in other words, it is possible to find, just choose arbitrarily a and b, or rather xa and xb, such that this condition is satisfied. Okay. You might think that this is trivial, so obviously we are going to next look at a case where I cannot do this trivially. Okay. But this is what we are ultimately trying to do, and if you think of it in the context of actual implementation of the data flow graph, what we are interested in is, number one, the dA, dB, etc. are given to us along with the data flow graph, so that tells us what needs to be implemented and what are the hardware complexities, the amount of time that will be required for each of these blocks to execute. We are interested in computing a value for t, that is the minimum iteration period under which this system can get executed, and we then want to find out what are possible values for xa, xb, etc., which will allow us to successfully actually execute this on hardware, right. In practice, those xa, xb, etc. will probably be some time instant, some clock cycle or something else, which is determined by some finite state machine controller, which says, okay, at this time instant, let this particular block start functioning. Okay. Or if you are talking about a fully combinational circuit, then there may not be a finite state machine controller, it is just going to be determined by, as and when one unit finishes, the next unit consumes its data and then starts executing, generates output, etc. Okay. That goes into a so called self-timed mode of operation.